Hello and welcome to the second video in our Essential Skills series. These videos are to help you to get to grips with physics and to prepare for paper 1, which is the physics paper. As you know, my name is Dr. Derek Fish. I'm Director of Unizulu Science Centre at the University of Zululand. In this part 1.2, we'll be looking at graphs. This is an introduction giving the theory behind the graphs, and we will then look at some practical applications with some real experiments. In your booklets, this is covered mostly on pages 6 and 7, but I encourage you to turn immediately to page 3 in your booklets. So remember, the page number is in my bottom right-hand corner, will be in your top right-hand corner. So if we look at the contents page, remember we are looking at 4 skills: graphs, free body diagrams, equations, and multiple choice and ratio questions. We are now focusing on graphs. And the reason for this is not just because we think it's important, but because the examiner does. And in the examiner's report, he noted that interpretation of graphs or graphing skills is a challenge for many learners. So I really hope that this video will help you get to grips with it. In this video, we'll look at the theory, and then we'll come back and look at 4 good examples of straight line graphs from experiments: motion graphs, the photoelectric effect, Ohm's law, and internal resistance. Looking on page 4 at the physics curriculum, what we've done is to underline all the sections which may involve graphs, and you'll see there are a lot of them. When we look at mechanics, in grade 10 you're introduced to the description of motion in words, diagrams, graphs and equations. Those graphs of motion are very important, and there's a prescribed experiment of velocity and acceleration time graphs and position time graphs. We'll spend a lot on that in video number 2. In grade 11, when you look at Newton's laws, the prescribed experiment on Newton's second law obviously involves graphs, in this case direct and inverse proportion. Grade 12, vertical projectile motion represented in words, diagrams, equations and graphs, and again the prescribed or recommended experiment, position and velocity time graphs for free fall. Moving on to waves, when we start with waves, they're represented as graphs, transverse and longitudinal waves, and especially in grade 12 the Doppler effect doesn't usually involve graphs, but it can also involve graphs. Moving to electricity and magnetism, particularly in grade 11, potential difference in current for resistor and bulb, Ohm's law, that involves graphs. We will do those experiments. And in grade 12, internal resistance is again the generation of a graph. Alternating current is represented by a sine graph as distinct from a straight line graph, and there's an experiment to compare potential difference graphs for alternating and direct current. Finally, matter and materials, the photoelectric effect. The experiment produces the kinetic energy frequency graph for the photoelectric effect. So there's lots on graphs in the syllabus. There's also lots on graphs in the exam, and you can particularly expect to find them in these questions. Question 3 on vertical projectile motion almost always involves a motion graph. And you can see the last 2 years you were given graphs. In 2018 you were asked to draw the graph. Question 10, the photoelectric effect. Again, the last 2 years have been graphs. Last year was the standard looking graph. In 2020, 2019 they changed the graph around and it caused a lot of confusion. We will look at that carefully in this video and in the video on photoelectric effect. And then question 8, it's sometimes question 9 in older papers, deals with electric circuits, and you can have graphs for Ohm's law or internal resistance. Again, you can see 2018 and 2019, there were graphs on internal resistance. 2018 one, again, they changed the axes, which caused a lot of confusion. 2019, you've got the step graph showing the voltage drop after the switch is switched on. Again, we'll look at those in great detail. Now, question 6 on the Doppler effect doesn't usually involve graphs, but it can. November 2020, again, a step graph showing the frequency falling as the sound passes the observer. 2019, there was a sine graph of the sound waves, which again was very badly answered. and we will spend some time on these graphs. And then question 9 on electrodynamics and alternating current, quite often sine graphs of the alternating current, like you can see in November 2018. Of course, question 1, which is multiple choice, can also involve graphs. Because each question only counts 2 marks, usually these will just be sketch graphs without any values. So look at a typical question. Here's a graph of an object in free fall. It's a rate graph. Something is graphed against time. And they say, which one of the following physical quantities can be the label? Now, obviously, this is something which does not change with time. So you need to ask yourself, which of these quantities does not change as an object falls? And of course, the answer would be C, the weight. Another multiple choice question, 4 possible shapes of graph for voltage against current. They're saying if it's an ohmic conductor, which would be the correct graph? And it must be B, because an ohmic conductor shows a direct relationship between voltage and current. And then finally, at the bottom of page 5, just a reminder about the skills. Now, these were covered extensively in the last video, but just a reminder that the examiner mentioned a severe lack of skills, especially graphs. And skill number 10, practical investigation skills. You will see that data collection is obviously what you use to draw your graph. B, general types of graphs and analysis. And C, identifying variables, independent, dependent, and control. All of these things are needed for successfully drawing and analyzing graphs, not just for Matric, but in life in general. So if you can turn with me in your booklets to page 6, a new page, and let's just look at an introduction to graphs. Now, the first question one should ask is, what on earth is a graph? Well, it's very easy to remember with 3 R's. Graphs show 3 things. They show the rate at which things happen, they show a relationship between variables, and they can show a visual representation of the data. Just a warning, which I'll come back to, that a graph is not a photograph. So let's start with the first part. Graphs show the rate at which things happen. And for this, we're going to do a live experiment using some fantastic equipment. It's made by Pasco Scientific in America, and it's distributed in South Africa by PERT Industrials. And again, I really want to thank PERT because they have sponsored the Science Centre with a large amount of this equipment. Now, we're going to do an experiment looking at the rate of temperature change. So let's do a real experiment. And experiments are the fun part of doing science, especially physics. So what you see on screen is not just a picture, it's a readout from an actual digital thermometer. Now, I have the thermometer over here. You can see it just looks like a steel needle, but this allows the computer to read the temperature. And you'll see if I hold it in my fingers so it gets warmed up, you'll see the temperature starts increasing quite rapidly. Now, I want to assure you that when South 32 needs to know the temperature in one of their pots or reaction vessels, they don't send someone to stick a thermometer into it. They have a probe like this permanently connected there, which gives the temperature all the time. And that can be read remotely. It can even be read by someone who's not at the plant. So let's have a look at some of the different ways that we can present the data. So at the moment, we have a digital display, and it shows us the temperature reading, and it's very useful for seeing what the temperature is, but it's not that useful for recording trends or to see how the temperature changes over time. So now you can see I've added a temperature meter, and this is much more useful for seeing if the temperature goes up or down. So if I hold the probe here so it gets a little bit warmer, you can see immediately that the meter goes up, and it's much easier to see the change and to see the rate of change. You can see it going up, and if I release the probe, we'll see the temperature start to go down again. But now, once again, this is not actually recording the data, it's just displaying the data for us, which is very useful, but won't help us to determine the rate of change. So now I've added a table to our display, and you'll see that as soon as I start recording data, this is taking one reading of temperature every second. You'll see that every second it records the temperature. And if I hold this so that the temperature changes, you will see that the table faithfully records the changes in temperature. So now we've got a record of all the data, all the different temperature changes as it goes up to almost 26 degrees. And if I release it and allow it to get cooler again, we can see that as it falls, every data point is entered into that table. So now I have 4 displays on screen: the digital readout, the meter, the table, and now I've included a graph. And this is a rate graph. It's a graph of temperature against time. And as I start recording the temperatures, you can see immediately the graph at the bottom starts plotting here. You can see the temperature is 22.5 degrees. And if I hold the thermometer in my hand to warm it up, can you see immediately the graph shows us so nicely how the temperature is increasing. And you can see that increase on the graph is very, very clear to see. So we'll just allow it to warm up to about 30 seconds. And then at 30 seconds, I'm going to release it and just allow it to cool naturally. Now, although we've got the data in the table, although we've got the meter here, although we've got the digital readout, I think you'll agree with me that the graph gives us the clearest picture of what is happening here. You could see the temperature was constant, you could see it increasing, and now you can see it decreasing. And we're going to allow it to record for a minute, 60 seconds, and then our graph gives us a very nice picture of what happened here. Okay. Now, let's do the experiment again, but this time, let's try to record a faster rate of reaction. So instead of just heating it up with my hand, I'm going to use some hot water and some cold water. So let's start a new set of readings. And once again, the temperature's gone back to about 20 degrees. You can see on the graph, the blue graph there is the old one. This time, after 10 seconds, I'm going to take this and I put it into a cup of hot coffee, and you can see immediately how the graph shoots right up to the top here. And you can see it's gone up to 70 degrees already, and it's heating up very, very rapidly. This time, to cool it, I won't just take it out of the hot coffee, I'll put it immediately into some iced water, and you can see the effect of that. In the iced water, it's going down, and it just keeps on going down here. We're going to allow it to go to 60 seconds like we did before. You can see it's getting very cold, actually almost close to 0, down to about 5 degrees Celsius. And we'll stop the recording there. So having taken 2 sets of readings, although we had all the data in the table, although we had the meter and the digital display, I think you'd agree with me that the graph gave us by far the nicest readout. And in fact, if I take this graph here and we just make it a little bit bigger so we can look at it properly, you can see the first readings were the blue one where I just heated it with my hand. The second one, the purple one, I allowed it to heat up in the hot water and then to cool down in the iced water. So what we can see very nicely is the different rates of heating and cooling. You can see from my hand, the rate of heating was very slow, and therefore the gradient of this line was not very steep. The rate of cooling was even slower, so the gradient of that line was even less steep. In the hot water, in my coffee cup, the rate of heating was very rapid. You can see by the very steep gradient. But then as it reached the temperature of the hot water, it started to flatten off. But as soon as I put it in the iced water, the rate of cooling was very rapid. So these are some real examples of rate graphs. And we're going to be doing a lot more experiments like this using this fantastic equipment from Pasco Scientific. Well, I hope you enjoyed that experiment. It's great to do live experiments, and we're going to do many more during this video series. And we will do experiments where you can actually record the data yourselves, draw the graphs yourselves, and come to your own conclusions. Let's talk some more about this idea of a graph which shows the rate at which things happen. One example of this is just a position time graph. And of course, the rate of change of position with time is just the velocity. So the green graph shows something that's traveling fast. So the rate of change is fast. The red graph, something which is traveling more slowly. With the red graph, it's always graphed against time. Secondly, graphs show relationships. And in this case, instead of a continuous time axis, we have discrete, we have separate values, and it relates, for example, values of pressure against values of volume. So a good example of this is Boyle's law, and we're going to do a simulation of the Boyle's law experiment. So here is a simulation. I trust you understand that this is not a real experiment like the temperature one was, but it's simply a computer simulation. But these can be very powerful. And for the teachers in your teacher pack, you do have a copy of the file. It's just called Boyle's law, and you can run this simulation yourself and try it as many times as you want. So here we have a gas syringe connected to a pressure gauge. The volume of gas between the top of the piston and the end is measured, and the corresponding pressure. Now you can see I can push the syringe in, and then when I release it, we get a reading of the volume, 21 milliliters, and the corresponding pressure. Now I can do this for another one and get a smaller volume and a higher pressure. I can also get a large volume and a small pressure. And I'm just going to do this a number of times, just quickly to save time, and generate a whole lot of data points for the table here. With this simulation, we have air inside the syringe, and we are simulating a whole lot of different data points. You can see my table is now full of data. Now, by pressing a button, I can convert those data points into a graph. And you can see very nicely when you look at the data points, we can see they clearly are arranged along a curve. And this particular curve we suspect is a hyperbola, an inverse relationship, pressure against volume. To check that, what we can do is instead of graphing pressure, I can graph 1 over pressure, the inverse, and you can see there the points arrange themselves in a very nice straight line. And that confirms to me that the relationship between pressure and volume is what we call a reciprocal or an inverse relationship. So these are discrete, they're separate data points, and with those data points, the graph has shown a relationship between pressure and volume. So that's the second type of graph. Graphs show rate and they show relationships between variables. Thirdly, graphs can give a visual representation of data. It can be a pie chart, a column chart, or different types of graphs. Now, please remember how important the title of your graph is. Imagine if this was a graph of pet club members' favorite food. That means people would rather eat dogs than eat cats. And of course, that's not what it is, but it's pet club members' animal preferences. You can read it from a table, but it makes much more impact when it's represented visually. Now, there's many different types of graphs, many different visual representations. You'll come across a lot of these in life science, particularly, not so many of these in your physical science paper 1. Now, I want to make a point very strongly because this comes up every year. And I've often been marking a matric exam, and the question will say something like, describe the motion of the green graph there. And students will say something like this. They will say, the car drives up to the top of the steep hill. Now, at school, all your motion is one-dimensional. It's left and right, or forwards and backwards, or up and down. There are no hills to climb. The fact that the graph goes up does not mean that the car is going up. It's a representation of position against time. Another example, if the question says, describe the motion shown by the red graph, some pupils would say the car drives up the steep hill, it drives across the top of the hill, and then it drives down the other side of the hill. Please make sure that your matric exam does not end in ruins by answering questions like that. A graph is not a photograph. So to summarize, graphs show 3 things. They show the rate at which things happen. Good example is a position time graph, shows the velocity or the rate of change of position with time. They show a relationship between variables. A good example is a pressure volume graph for Boyle's law. And they can show a visual representation of the data like in a pie chart. And again, a reminder that a graph is not a photograph. I've been amazed at just how much graphs come into our world today. It's amazingly, just looking at my cell phone, how many graphs I find there. For example, there's a graph of my mobile data usage. This is just a screenshot from my cell phone. It's a graph of usage against time. So it's a rate graph. If I go for a walk, my cell phone counts the number of steps. On the 26th of July, I did 11,304 steps, a distance of 8.12 kilometers. And here I have some graphs which show at what time of day I was walking on the 26th, and they compare my distance walked on the 26th with other days. If instead of walking, I go cycling, again, the cell phone records all the information about cycling. And here's a graph of my speed at different times, and also the elevation, the steep hills that I climbed. And then finally, you can get even more information, like, for example, how long did it take to do my first kilometer, my second kilometer, which was my fastest kilometer. And all of this is just on my cell phone. So it's so important to understand graphs if you're going to be living in the world today. So what sort of graph skills might you be expected to utilize in your matric exam? A little bit lower down on page 6 is a list of 4 graph skills. 2 with drawing graphs and 2 with reading information from graphs. You might want to copy down the references in the brackets at the end of each point, because those are not in your booklet. Now, these will make more sense if we look at actual examples of them. So let's go straight ahead. Skill number 1. The skill is to be able to analyze and explain trends in a given sketch graph. The example given is question 3.5 from November 2019. It's on page 15 in your books if you want to look, or you can just look on the screen. So projectile motion very often involves graphs of motion. Sometimes you have to draw them, but in this case you have to analyze one. It's a sketch graph. You'll see it's not drawn on blocked graph paper. It's not to scale, and no values are given, just letters. And don't worry about the details of the question, but you're asked to identify by letters A to H different times and different positions during the stone's flight. So that's the first type of graph. Secondly, you might be asked to read values, including gradient and intercept, from a given accurate graph. An example, question 3.2 from the November 2020 matric exam, is on page 16 in your books. It's a bouncing ball, one of the favorites of the examiners, and this is an accurate graph. Although it's not drawn to scale or on graph paper, there are values, and you are asked to make calculations based on these values. For example, 3.2, use the graph. In other words, don't just solve equations, and determine the time the ball is in contact with the floor before the first bounce. Now, it's quite easy if you look at the graph. The ball landed at 0.64 seconds, took off at 0.67. The difference between those times is 0.03 seconds, and that's the answer. And if you know how to use the graph, it will not be difficult. And you continue using equations of motion to take values off the graph. Finally, you're asked for the time t indicated on the graph. So those are 2 skills involved with reading values or analyzing graphs. You might also be asked to draw a graph. So skill number 3, to be able to draw a sketch graph of a situation. This is question 3.4 from November 2018, and it's on page 14 in your booklets. Again, don't worry too much about the details. A ball is thrown vertically into the air and it comes down again. You have to do various calculations, but 3.4 requires you to draw a velocity time graph for the motion of the ball. It's only 2 marks. It's a simple sketch graph, not to scale, but you are asked to indicate the initial and final velocities and the time taken to reach the highest point. And then finally, this is quite uncommon, but you might be asked to plot an accurate graph on graph paper provided. So you can see in your exam answer sheet was given this sheet of graph paper with blocks. The axes and scales were drawn in. Please notice the different scales for volts and current. This is an internal resistance experiment. 812 says please use the information in the table that was given in the question. Plot the points, so that's one skill you need, and draw the line of best fit. Now when we get to internal resistance, in video 4.2, we will do an experiment and plot two graphs, which will teach you the skills that you need for this. Although that's only 3 marks, you're then asked to use your graph to answer the next 2 questions without using equations. So it is very important to get your graph correct. So 4 skills which are very important using graphs in your matric exam. Now, what about different types of graphs? We're still on page 6, but you won't see this. What you will see is a list of different types of graphs which you encounter in mathematics. So let's consider where these graphs come up in science. First of all, a constant graph, linear or quadratic graphs. All of these are types of motion graphs. Your acceleration time graph is always constant at school. Velocity time is often increasing because of a constant acceleration, and that would give you a quadratic increase in position. Now, just think of the graph we've just looked at, question 3.5 on page 15. If you look at the shape, these are quadratic graphs. The parabola is upside down, but this is exactly this type of graph. Nextly, what about the hyperbola or reciprocal graphs? There's 2 examples that are common in school science. One is pressure versus volume for Boyle's law. The other one is acceleration versus mass for Newton's second law. Just note, in physics, we usually just work in the first quadrant because most of our values are positive. Don't neglect the sine graph or think it's only for trigonometry. The sine graph is extremely important in science. Anything that is rotating, anything that travels in waves can be described by a sine graph. So your electromagnetic waves or your alternating current. Now, once again, if you go to page 48 at the back of your books, you will see the November 2018 paper and June 2019, both of them contained a sine graph of voltage versus time to show alternating current. Finally, these 4 types of graphs, circles or ellipses, cubic, exponential, and logarithmic, they are quite legitimate graphs in maths and in university physics, but at school you'll be unlikely to encounter these graphs in school science. Now, I'd just like to mention one other type of graph. This is not in your books, and that's why the page number is in red. But in 2 particular laws, the Coulomb law and the gravitational law, you'll come up against an inverse square law, where force is proportional to 1 over r squared. Now, you can see by the red graph, as r increases, the force decreases very dramatically. And that's why electrostatic and gravitational forces are not very powerful over long distances. Just for comparison, I've also plotted the blue dotted line, which is simply a hyperbola, an inverse law. It also gets less, but not as fast as an inverse square law. Now, you might want to think about, why does this get so small so quickly? And of course, when a force is felt at a distance, it has to operate over an area which increases. Now, because area has to do with the square of the side, and the force is now spread over a much larger area, that is why this force tends to decrease so very quickly. So at the bottom of page 6, how do you go about drawing a graph? Maybe all of this makes sense to you, but you've never actually drawn a graph and put some data down from an experiment into a graph. Don't worry, we're going to do lots of examples, but let me tell you a general method. All you need to do is remember the word TALSIP. Now, of course, that's not a real word. It's a made-up word, but perhaps that'll actually help you to remember it even better. It's an acronym, and each letter stands for a different word. So when you're going to draw a graph, start by choosing an appropriate title. That might be current versus voltage. Then A stands for axes. Select the variables to go on the axes. Decide which is the dependent variable for the vertical y-axis and the independent variable for the horizontal x-axis. L stands for labels. Make sure you label your axes with units. So voltage in volts, current in amps. S stands for scale. Please don't draw your whole graph in one little block in the corner of the paper. Scale your graph to fill as much of the page as possible. I stands for intervals. Use that scale to determine how much each small block equals. And this is also important in interpreting graphs. we will do some examples on this. P stands for plot. Plot your data from the table onto the graph, carefully checking that you don't mix up your X and Y points. And finally, the last P, plot the best fit line or curve for the data points. Calculate intercept and gradient. Now, this will make a lot more sense when we do some worked examples. And as soon as we get onto experiments, we will do just that. So don't worry about that. Let's turn over to page 7. And let's look at some theory on straight line graphs. Now, this is theory that you should have covered a few years ago in mathematics, but it is very important. So let's assume that we don't all understand straight line graphs perfectly, and let's recap this. Now, from mathematics, you should know that the equation for a straight line graph is in the form y equals mx plus c. The graph looks like this. It has two variables. Y on the vertical axis is the dependent variable, and x on the horizontal axis is the independent variable. There are also two constants. M is the gradient or slope, and c is the y-intercept. So we can summarize it in a table like this, and I'm going to show you in the exam questions just how important defining this equation and this table is to answering questions correctly. So two variables in red, and you need to identify what is going to change and what will be constant. The y variable is dependent on the x variable, so it's the result of the x, and we can't decide what it should be. But the x variable is independent. It will be on the horizontal axis, and we can adjust it as we like. So when you have time as a variable, it's mostly on the horizontal axis because time just carries on and is not dependent on anything else. Two constants, the gradient, which shows how steep the graph is, and then the y-intercept shows where the graph cuts the y-axis when x is equal to 0. Now, I think this will all make a lot more sense if we have a look at a simulation. And this is a simulation from PHET. Now, if you just Google PHET, it'll immediately take you to this website. But again, in the teacher pack, this particular simulation that we're going to do is provided for the teachers. PHET was devised by Nobel Prize winner Carl Wieman, and it was founded in 2002 from the University of Colorado in Boulder, and their simulations are fantastic. But again, don't just take my word for it. In the 2019 National Exam Report, the examiner wrote, teachers must include the use of ICT during teaching of science, especially software such as PHET and their simulations. This was recommended by the National Examiner. We're going to look at a particular simulation called graphing lines, which, as I said, is provided for you in the teacher pack. And this will really help us to understand how straight line graphs work. So let's have a look at this wonderful simulation from PHET. It's called graphing lines, and here you can see a simple straight line graph. It's a graph of y equals x. That means for every point on the line, the y value is equal to the x value. If I put this to a point on the line, you can see -7, -7, -6, -6, -2, -2, +5, +5. X and y are always equal on the line. If I take it off the line, then they're of course not equal. Now, the two important things, once again, our variables are y and x. They can vary, they can change. Y is the dependent variable on the vertical axis, x the independent variable on the horizontal axis. Then we want to consider m and c. So let's start off with c, which is the y-intercept. And I think it's easiest if we just make our line flat. At the moment, this is the line y equals 0. It cuts the y-axis where the purple dot is at 0. And if I move that up and down, you can see y equals 3, y equals 4, y equals 5. I can also just change the number here, and you can see the effect of increasing or decreasing c is to move the graph up or down. So c tells us where the graph cuts the y-axis when x is 0. At the moment, this line is flat, the gradient is 0. But if I pull that blue ball up, you can see when you go across 3 squares, you now go up 1 square. So the gradient is 1 over 3 or 1/3 x. If I pull it up again, 2/3 x. Pull it up again, 3/3 or just 1x. And of course, the more you go up for the same distance across, the gradient gets steeper and steeper and steeper. So there's the gradient of 3x, which is obviously 9 over 3. Now, of course, a gradient of 0 means a flat line, and you can also have negative gradients. And if I pull the ball down here, you can see when you go across 3, you go down 3, or you can say up -3. So the gradient is -3 over 3, which is just -1. Now, of course, if I increase the c value now, the y-intercept, you'll see the whole line moves up like that. So this is the graph of y equals -x, that's the gradient, plus 3. Now, if I also put on screen the graph of y equals -x, you can see these two lines are clearly parallel, and that's because they both have gradients of -1. Now, once again, this fantastic simulation is in the teacher pack, so teachers, please allow yourselves in the class time to play with it. There's lots you can learn about straight line graphs, more than we have time to do now. It's got various other functions at the bottom, including a great line game. And they will give you a graph like this. You have to try to fit your line onto the graph by moving it up or down. So let me try, let me move my line there. Let me check if it's correct. Oh dear, it seems I need to try again. So this is a fantastic game which will help you learn a bit more about these line graphs. So let's summarize what we've learned from this PHET simulation. And this is on page 7, the summary is there. But a straight line graph, again, your two variables, y and x, and your two constants, m and c. M is the gradient. It's the rise up over the run across. And you can see here, in this case, it goes up 6 blocks and across 4 blocks. So you get a gradient of 6 over 4 or 3 over 2. And you find it by subtracting the lower y value from the upper one, and then subtracting the left-hand x value from the right-hand one. So gradient just tells you for every block you go across, how many blocks you go up or down. The c value is the y-intercept. It's where the graph cuts the y-axis at the point where x is equal to 0. And in this case, it's c is equal to 2. So our equation y equals mx plus c becomes y equals 3 over 2x, that's the gradient, plus 2, that is the y-intercept. Now, a couple of special cases, and I showed you this on the simulation. First of all, if you have a horizontal line, the graph is just y equals a number, and m is equal to 0. There's no x term in the equation, because it doesn't matter what x is, y will always be 5 on that line, and always be -2 on this line. Now, you will see these quite a lot, particularly your acceleration time graphs are usually horizontal straight lines. Another example could be if acceleration is 0 and this was a velocity time graph, your velocity would be constant, so it would be represented by a line like this. Remember that in physics, we usually only work in the first quadrant, as we're only working with positive values. One other special case where c is equal to 0, the graph will go through the origin, and you'll just have y equals mx, y equals the gradient, times x. Now, in this case, that means that y and x are directly proportional. That means if you double the value of x, you will also double the value of y. So an example of this would be a graph of velocity versus time, when the initial velocity is 0, because then if you double the time, you would double the velocity. Now, in the next video, we will be looking at graphs of motion, and many of these things will become apparent. Now, perhaps these graphs are still a little bit theoretical to you, and maybe it would help you to look at some graphs of a kind that you might expect in real life. So let's look at an example of a monthly cell phone bill versus minutes used. We're still busy on page 7, but the red page number will tell you that you don't have this in your books. In fact, we're going to do an exercise, so please get some paper so you can write down what is here. So how would you draw a graph of monthly cell phone bill versus minutes used if the calls were charged at 3 Rand per minute and there were no other charges? Well, we have a title for our graph. Now we need to label our axes. So the vertical would be the bill in rands, because that's dependent on the talk time in minutes. Now we'd expect our graph to be a straight line through the origin, because these two are directly proportional as there are no other charges. Our gradient would be 3, because calls are charged at 3 Rand per minute. And our C value would be 0, because there are no other charges. So y equals mx plus c. In this case, we'd say our bill is 3, that's from 3 Rand a minute times the time in minutes, plus 0, or we could abbreviate that to b equals 3t. So there you have the graph, the constants, and the equation. Now it's your turn. Here are 3 graphs, and I'd like you to draw these in your books, and I'd like you to try to draw the graphs. I'd like you to try to write the equations and determine the constants for these 3 cases. So the first graph, I've given you a dotted line for calls charged at 3 Rand a minute. I'd like you to draw a graph of bill against time if calls were charged at 2 Rand per minute. Also to write the equation and the constants. The second case, a bit more tricky. Calls are charged at 2 Rand a minute, but there's a fixed contract cost of 100 Rand per month. So even if you use no talking time, you will still pay that 100 Rand. What would the graph look like? What would the equation and the constants look like? And thirdly, a third scenario, if calls are charged at 3 Rand a minute, but your first 10 minutes are free. How would you graph that? Write an equation and determine the constants. Now at this stage, teachers, please pause the video here. I think 6 minutes will be quite enough to try to complete these graphs, equations, and constants. So pause the video, don't just go on to the solutions, because it's very important for you to try it yourselves before proceeding. So I'm hoping that you did in fact pause the video and you've all had a try. So let's have a look at some answers here. Let's look at the first one. The dotted line, remember, was the 3 Rand a minute charge. What would it be if calls were charged at 2 Rand per minute and there were no other charges? Well, let's label our axes. That's the bill in rands on the y-axis, time in minutes on the x-axis. We'd expect our graph to have a lower slope because it's only 2 Rand a minute. Our gradient would be 2. Our C value would be 0 because there's no other charges. So there's the constants. And our equation would simply be B is equal to 2 times T. Let's look at the next example. Calls are charged at 2 Rand per minute. So we'd expect a similar looking line, but there's a contract cost of 100 Rand per month. Again, we label our axes, the bill in rands, time in minutes. But now our graph is going to look like that. The gradient is still 2, but the C value is 100, because even when the time is 0, you're still going to pay 100 Rand as a contract cost. So there are your constants, M equals 2, C equals 100, and your equation would be B equals 2T plus 100. Let's look at the third example. Calls are charged at 3 Rands per minute, but the first 10 minutes are free. Again, label our axes, bill in rands versus time in minutes. And now our graph is going to look like that. And the gradient would be 3. So I've made it dotted to remind you that it's the same gradient as that first graph. Lines which are parallel have the same gradient. Now, it crosses the x-axis, the time axis at 10, but I haven't put that in blue because this is in fact not the C value. M equals 3. I want you to think a little bit about what the C value is and perhaps pause the video and try to calculate it before I go on. The equation is B is equal to 3 times T minus 10. So we subtract 10 from the time before we calculate the bill. So a slightly different looking equation. So have you worked out what C should be? Well, C is 3 times minus 10. So C would in fact be minus 30 in this case. Now these were just some real life examples which were probably easier for you to understand, but do you realize that these are just actually your physics graph? The first graph could easily be an Ohm's law graph, current in amperes versus voltage in volts. And the gradient of the graph is just 1 over R, where R is the resistance. So a large resistor would have a small gradient, and a small resistor would have a larger gradient. Ohm's law, V equals IR. If you solve for I, we get I equals 1 over R times V. So gradient 1 over R, C equals 0, because current and voltage are directly proportional. The second graph you did is just a velocity versus time graph with final velocity versus change in time. And the C value is just the initial velocity there. The gradient in this case is the acceleration. So you can see that M and C become very important because they actually have real life values. Your equation would be final velocity equals acceleration times change in time plus initial velocity. And finally, the third graph could easily just be your photoelectric effect graph with energy in joules on the vertical axis, frequency in hertz on the horizontal axis. And this value, not the C value, is now F0, the threshold frequency. And the gradient in this case is just H, which is Planck's constant. So your equation E equals H times F minus F0, you subtract that. If you multiply it out, you get HF plus minus HF0. So that is your C value, minus HF0. And that's actually just the negative work function. I'm sure you found it easy to understand the cell phone graphs. And I want to tell you, these graphs are no more difficult to understand. And don't worry, we'll be spending quite a lot of time on each of these graphs. Let's do one more practical example. Let's have a look at a graph where something is decreasing. So remaining airtime versus minutes used. If the calls are charged at 2 Rand per minute and your initial airtime was 200 Rand. So we're expecting to see a graph which is decreasing rather than increasing. Now, once again, I'd like you to pause the video here. I think 4 minutes should be plenty, and try to complete the graph, draw the line on the graph, complete the equations, and determine the constants M and C. So go and pause the video here and go and have a try. Right, so I hope that you all tried it, but let's have a look. First of all, the line on the graph. Well, we would expect something which is decreasing because the more you talk, the more your airtime gets used up. The initial airtime, which is the C value, was 200 Rand, and the gradient is minus 2. Calls are charged at 2 Rands per minute, but your balance is decreasing, so the gradient is minus 2 rather than 2. So the graph would be airtime equals 200 minus 2 times time, or we could write it as airtime equals minus 2t plus 200. Now, once again, I'm sure you could understand this graph very easily, but I want to tell you this is really no different to the physics example of internal resistance. You have the equation V equals minus R, where small r is internal resistance, times current, plus EMF. Our variables are voltage being dependent on current, which is independent. The C value, the y-intercept, is simply the EMF of the battery, and the gradient is minus R, where R is the internal resistance of the battery. Now, I mentioned to you earlier on that 2 questions which were answered very badly in the November 2018 and November 2019 exams both involved graphs. So let's have a look at them. We'll just look at them quickly today, but don't worry, we'll come back to them in much more detail. So remember this graph and how it looks for internal resistance. And in November 2018, the examiner confused everybody by changing the internal resistance graph. Remember, this is what you had, voltage versus current, with the C value equal to E and the slope equal to minus R. Remember that. But this time it was rewritten in this form. As a result, this was the worst answered question in the whole paper. The national average for this question was 35%. Now, how do we get around that? Well, it's really not difficult. Always start with the standard form, y equals mx plus c. Identify your 2 variables and your 2 constants. Now, in this case, the equation was given to you in the exam. Your variables are r and 1 over I, not I. And your constants are EMF and minus r. And again, it's helpful to put them in the table, which we showed you earlier. Now, what confused everybody is that M and C were swapped around from what they usually were. So in this case, the gradient was EMF, and normally the gradient is minus R. In this case, the y-intercept was minus R, where it's usually the EMF. So as I said, it really isn't difficult to answer these questions. 921, write down the internal resistance of the cell. Well, we know that C is equal to minus R, so one simply reads off the graph minus 3 ohms. Secondly, calculate the EMF of the battery. We know that the gradient is equal to EMF, so you do a calculation using the graph and the graph paper to calculate gradient, and you calculate the EMF. It was not difficult, but on these two little questions, the national average was 33%. Now, another bad example on page 19, the photoelectric effect graph, the worst answered question in the November 2019 paper, question 10, national average 38%. Now, people were used to the graph, which had energy versus frequency, but again, the examiner turned the graph on its side, so it looked different. But it's not difficult if you simply follow the proceedings. Our standard form y equals mx plus c. Put it into that form, and we have energy of photons equals half mv squared. V squared is the x, plus w naught, the work function. Now, this equation is not new to you. You can find it in your data sheets, and in a couple of weeks' time, we'll look at this question in a lot more detail. Again, put your variables and constants into the table like I showed you. So your y variable is energy, your x variable is v squared. That tells you that the gradient is half the mass of the electron, and the c value is the work function. Now, once you've done that, it makes the questions quite easy to answer. And yet, only the average for question 10.2 was 29%. For 10.3 was 13%, the national average, and for 10.4 was 34%. This question was very badly answered. But let me show you how easy it is. Calculate the work function. Well, the work function is just the c value, so I can read it off the graph. It's 7.48 joules. That's not difficult. Which physical quantity can be determined from the gradient of the graph? Well, the gradient is simply half the mass of the electron. And calculating the value of x when you have this equation is not difficult. Now, maybe you found these last two examples a bit hard to swallow. Don't worry, we're going to go back into them in much more detail. What I really wanted to show you is how important it is to understand straight line graphs, the standard equation, and the x and y and m and c values. So I hope it was helpful for you to learn a bit more about graphs, especially the mathematical basis for graphs. As you saw in those last two Matric questions, they caused real problems with pupils in the exam. And the problem was not based on the science, the physics. The problem was simply based on manipulating the graphs mathematically. And that is something that you can learn. So I really encourage you to go through this video again if necessary. But we will be applying this to 4 different physics systems, to motion graphs, to the photoelectric effect, to Ohm's law, and to internal resistance. And when you do the actual experiments with me, you will understand so much better how the graphs work and how they display the data. Apart from your matric, as you can see in these pictures, graphs are needed at all stages of life in the 21st century. And I really encourage you to make sure that you can use, manipulate, and understand graphs. And I want to tell you that'll give you a step ahead in the job market as well. So I hope you continue with the series. And don't forget to watch the short interview which follows this with a prominent personality in physics in South Africa. So I'm excited to have the opportunity to be speaking to Brian Massaro, who's the CEO of the South African Institute of Physics. Hello, Brian. Can you just tell us a little bit about yourself, where you're from and what you studied?
Okay, thanks for the opportunity, Derek. I am from Zimbabwe originally, and I grew up there in a rural area and went to a school in a rural area. Even my secondary school, I went to a rural mission school. Then I studied physics, BSc honors, MSc honors in applied physics at the University of Zimbabwe. Then I also did an MBA there. But as you know, we always continue to learn. Now I'm doing a doctorate in business leadership in technology foresight with the University of South Africa.
That's fantastic. In fact, as you know, I only finished my PhD 3 years ago. So, Brian, what is your current position? And can you tell us what the Institute of Physics is?
Okay, my current position is I'm the CEO, which is the head of the South African Institute of Physics. And the South African Institute of Physics is the professional body for physics in South Africa. And the mission is to be the voice of physics in South Africa. And you know, physics is the basis for all science, engineering, and technology. And they say physics plays the role of canary in the mine. So when physics is sick, the whole science and technology is sick. So SIP's role is to ensure that physics in South Africa stays healthy and of world class.
Fantastic. Now, you know that with these videos, I'm preparing Matric students for paper 1, which is the physics paper. So
Yes.
Why do you think physics is important in our world today?
Okay, physics is important because it is the basis for all science, engineering, and technology. And the physics of today is the technology of tomorrow. So if we have more physicists, then we can improve our world, we can improve the quality of our life and a lot of things. For example, the research that we are going to be doing, the way the physicists are going to be working, and physicists are imparted with problem-solving skills which are required in all the sectors of science, engineering, and technology.
Fantastic. Now, you're aware of the fact that the matrics of 2020 have had a tough time. So can you give them a word of encouragement before we close?
Okay, we encourage them to get in touch with us, the South African Institute of Physics. We are preparing some materials together with partners like yourself, which they can use with their teachers to revise for their exams and then prepare. And then they have to know that everyone is a genius, and genius is just 1% talent and 99% hard work. So they have to study and review their work, then apply what they have learned, then practice and time themselves. And as we say, physics is the art of solving problems. They have to start learning to solve problems using the mathematics, algebra, graphs, and equations that they learn. And no matter how dark the night is, the sun will always shine. So this COVID will pass away, and we wish them all the best in their matric exam preparations.
Thank you so much, Brian.